So today I would like to coin a little bit the term perceptual display. And the idea would be to use some insight from perception in order to improve apparent quality of images. So we observe that displays those days are getting better and better. If you look into SIGGRAPH proceedings, last couple of years, you will have even specialized sessions on displays, HMD, movie-oriented displays, maybe sometimes related a little bit with fabrication. That's a hot topic. People build displays themselves. There are some startups, so by buying some off-the-shelf pieces, you can make some improvement. But I would not like to talk today about building displays. I would like to focus on some observation that is very likely will be still limited in terms of reproducing certain parameters from the real-world observation. Yes, in terms of contrast, brightness, temporal resolution, real world is continuous. Yes, we discretize it in temporal spatial domain with pixels. Also, in terms of depth processing, there will be some limitations. There are no known displays, commercial displays. They do accommodation, at least as far as I heard. There are some attempts to do this in academia, some building some prototype. But that's also important visual cue when we observe real world. As I mentioned, I would like to take advantage of certain properties of visual system, and I would like to improve all those qualities that I mentioned. In particular, I will focus on those in the frame, and for completeness, I will very briefly go also over contrast and brightness. So some of you perhaps heard about Cornsweet Illusion, and the idea here is that luminance signal is marked by this blue line, but what you rather see is maybe similar to this dashed green line to convince you. Yes, I included this discontinuity now, and the level of luminance on both sides is the same. So this illusion disappeared. Yes, so essentially the idea here is that we create some event, some contrast, and human brain fills in. Yes, that's the most likely scenario. And how we can use it? We can use it as artists do. Yes, they introduce Cornsweet illusion into their paintings because they're in permanent need of dynamic range. This is why they introduce such Cornsweet profiles. So in tone mapping, we do very often good job in terms of even enhancing contrast. Some of you may not even like it. Let's assume that we have image like shown here. That's kind of gradient domain method that emphasizes on local contrast. But we lost on the way some contrast between horizon, sky, and buildings. Yes, and we can restore this contrast by introducing Cornsweet profile. Dark blue means darkening, red means brightening, and we have this effect. Another illustration. It would be good to reproduce really deep shadow, dark regions, but still we get used that in shadow we can read. Yeah? So we can introduce Cornsweet profile on the boundary of shadow, and this way, without losing much dynamic range of the display, still be able to read text in this shadow region. So we should be careful. Yeah? So Cornsweet illusion, when we add it a little bit, can sharpen images, can improve contrast, what I demonstrated. But when you exaggerate, you will have halo effects. So how perception can help us? Of course, help us that we use this illusion at all. But we can do a little bit of study, visual study, like Rafał Mantyuk and his team did. And here the associated idea is that we go over two parameters, spatial frequency and magnitude of this enhancement. And then you can see that we add a little bit of this effect that's below threshold, we just don't see. So that doesn't matter. In some region, in terms of this magnifying parameter lambda, that's just right. We get nice effect. And then when we exaggerate, we have halo effects. And those halo effects will be more visible for higher frequencies. So that was quick trick about enhancing contrast. Yeah? So now about brightness. And so when you look on this cross on your right side, yes, you get the impression that this image is glowing. Yes, there is no light source here. Yes, that's purely reflective screen. But nevertheless, by introducing those smooth gradients, you have this impression. Artists, again, would use it very widely, and we will try to emulate this effect. So why this illusion works? Yes, because when we are exposed to very bright side, we have imperfect optical paths of light. So lens has some impurities at the towards the periphery of lens. You have something like diffraction net, and you have also some particles suspended in aqueous humor. All those effects cause diffraction. So essentially, when you look into bright light source, yes, then on the retina you get image with these scattering patterns. Yes. So essentially, when we draw directly on our retina such pattern, our brain is a little bit fooled and thinks that that's a bright light source. So we just add such typical diffraction patterns that are simulated using kind of simple, very basic wave optics. And then the idea is, of course, we can enhance illumination. In games, you would just use a set of Gaussians to get some desirable profile. Maybe if you do this more carefully, you may simulate once this effect and make Billboard, or just convolve all pixels, in particular those bright ones, with this scattering pattern and get this effect. Now I would like to talk about temporal resolution. So when you look into those two bars, the only difference between them is the refresh rate. And then immediately the bar that is refreshed with 30 Hertz looks quite a bit blurred. Yes? Let us do another experiment. Please try to follow those columns as they move. And I would expect that you see them quite a bit blurred. And now maybe this blue line will be useful for the first time. Please focus on this blue line. And then image should look sharper. Yes? So this arises in your brain. Yes, I don't make any tricks that I sharpen or blur those images. This is purely how you behave. Either you track with smooth pursuit eye motion moving pattern, or you let it go over your retina. So what's the idea? That's discrete world. Yes, in reality, we are pretty good in tracking moving objects because we want to keep them at the center of fovea. Yes, only there we can get super high resolution, and if we would have some predators, we would like identify them exactly, know who they are and at what position they are. This is why our smooth pursuit eye motion, so-called, is very precise. In discrete world, smooth pursuit eye motion remains the same. On the screen, we follow object with high precision. The problem is that for certain very short time, some milliseconds, 60 milliseconds, say for 60 Hertz refresh rate, those images may be frozen. They are frozen, but you still continue tracking them. This is why on your retina, you get blurred image. So when I ask you to follow those columns in this building, this is exactly what happened. Yes, image was frozen at a certain moment of time. You continuously move trying to track it. This is why you have this whole type blur effect. This whole type blur effect gets more and more important to consider. At CRT time, there was no problem at all. Yes? Now we are at LCD time. They are much brighter, and then we are more sensitive for it. You get higher and higher resolution, and then manufacturer asks you to get closer to the display to enjoy this high resolution. Doesn't make sense to buy high resolution display and sit many meters away. Yes, you just don't enjoy those details. When you get closer to the display, then immediately when you follow some objects moving on this display, your smooth pursuit eye motion is performed with very high angular velocity. So you have more and more whole type blur. So what TV manufacturers would do, and maybe you saw in some shops, yes, you will get 200 Hertz TV or even 600 Hertz TV. Okay, we will use 120 Hertz display, and we assume that we render frames with 40 Hertz, like in TV signal you have 60 Hertz, and then they would replicate it, calculate it using optical flows of intermediate frames. We will do similar thing, yes, but what is our trick? We will just use image-based rendering, yes, in image synthesis we have depths, we can do work with high quality. But those who did the image warping, they know that sometimes there are some imperfections there, yes? So what we are going to do, we will blur out our image. So you may find it a little bit paradoxical. I would like to fight against whole type blur, and actually I would blur some of my images. Yes. So what's essentially the trick? So here we have an original image, and those two are in between images that I work, and I remove high frequency from them. Then of course I would have deficit of high frequencies. This is why I will enhance high frequencies in original image. This image is calculated, has high quality, and there is no problem to pump up high frequency. So overall, the balance of high frequencies will be there. Some images in between will be blurred. When your eye integrates this signal, you would be happy. You would have enough high frequencies. And additionally, those high frequencies, of course, on technical side, you should avoid some signal saturation close to the 0 level or 255 ADP kind of encoding. But that's the kind of less important. So we'll have over-sharpened image and two blurred images. This over-sharpened image is shown for you for a very short time. And this reminds how CRT display works. CRT display works, it blinks through this scanning all pixels, yes, some details for a short moment of time, and there is no whole time blur. So in some sense, that's a very similar idea that we have here. Still, let us stay in temporal domain. You know that regular movies are recorded with 24 frames per second, and then frames are 3 times replicated, so that you don't see flickering. And Hobbit trilogy and Cameron has plans, and such films already happened. They're recorded with 40 frames per second. We are technical people. Okay, we would be happy, yes. We know we avoid many technical problems, yes. But moviegoers, especially those traditional, they would complain. The appearance of movie changed for them. And it changed in the sense that it reminds rather this cheap video recording soap opera kind of style or look. So on technical side, things gets better. Subjectively, people are unhappy. And in particular, when we have a kind of panning camera motion or some object motion in the movie. So I don't remember exact number, but in the cinematography, there is some rule how quickly some object can move over the screen. Because if it moves too quickly, the faster the motion, then of course you have more this kind of stabbing and juddering effect. This is in particular visible for this kind of panning type of motion, but statistics says that over 10% of shots use just some form of panning. Okay, so essentially what we would like to achieve. We would like to give artists freedom. Okay. Why stick to 24 or 48? Yes, please choose anything in between, and moreover, please choose it locally according to your wish. So some part of objects will be 48, some parts of film of a frame would be 36, 27, whatever, smoothly change. Yes. And why it is good? Because this may give some new expression tool for director. Yes, I mean there was such a movie recorded by Disney, and they use explicitly 2 different frame rate continuous, yes, like showing current situation and coming back to the past. Yes, just that you have like this mental separation. Yes, maybe you even don't realize, but you feel something change. How we are going to achieve this smooth frame rate manipulation? So in the real world, again, we have continuous signal, we sample it, yes, and let's assume that we have 48 frames per second, and for simplicity, let us not consider the full frame, but let's focus on 1 pixel. And over this pixel, we have such signal in temporal domain, yes. And then, of course, we discretize it. We will use some certain exposure time, 180 degrees, maybe half time exposure is closed, shutter is open, and half time shutter is closed. We have camera working at 48 Hz, we have display, we just display, yes, nothing special happens. Let us consider situation like related with movie, but our display still remains 48 frames per second. We just display twice certain all frames, and problem is solved, yes. But now if we would like to take more exotic number of frames, we have situation that maybe for 3 captured frames, we need to display 4 frames. So this means that certain frames will be directly displayed, but time to time we need to display certain frames twice. And again, I refer to this smooth pursuit eye motion. We are very good at tracking some object. And what happens here is that we have smooth motion, and then at a certain point it freezes for a bit longer. And then smooth motion and freezes a little bit longer. So always when I display 2 frames, I have this problem. And that's kind of judder. You witness this, yes, because very often like movie films are converted to 60 Hertz, yes, from 48 they go to 60. So this problem happens there as well. So what is our trick? And this is the only exception during this talk. This time I will talk about make image quality worse, not better. But some people would like it. We avoid soap opera look. Technically it's worse, but people like it better. So what we are going to do, we will shift the moment of time when we perform something our frames. Yeah, so technically we will still record them 48 Hertz or render 48 Hertz, and then we will warp them, and the amount of warp shifting them closer would correspond to the amount of judder flickering that we'll introduce. So we will spoil in controlled way image quality, and then at the end we'll get to the quality and ask for 24 Hertz refresh rate. Yes, so essentially we found this mechanism to do it. Yes, this is in terms of look, emulation of 36 frames per second. Those integration kernel are just placed in temporal domain as shown here. Yes. So what's going on behind the scene? Yes. So let's imagine that we have some bar, as we show, as you have seen in those videos, that moves from left to the right. Yes. And this, let's assume that it moves in continuous world. Yes. So we have continuous signal. You track this moving bar, so you stabilize it on your retina. Yes, and that's exactly the situation. And here is discrete world. A bar is moving, no stabilization, and here bar is moving, we stabilize it. And at high contrast edges, your photoreceptors would integrate exactly this signal. Yes? And because of this, you would see this flickering. Yes? When I show this panning sequence, you have a lot of instabilities, a lot of flickering. So what can be done? We have 48 Hertz refresh rate, and somehow we didn't prove it, but intuitively the area of this white and purple region, the ratio between these determines the amount of all this judder flickering, all those negative effects. So when I reduce the refresh rate directly by some factor R, I increase this area. Yes? So this becomes more apparent, and this is what we see at low refresh rate. This becomes more apparent, and also the resolution of flickering gets lower. It gets lower, it's more visible. 48 is almost close to a critical flicker frequency, when 60 it is in fact this critical flicker frequency, but this flickering becomes less visible. And by shifting our frames in time, we, in some sense, control both this area and both corresponding flickering. So what remains to be done? We need somehow to get some knowledge how much we should shift our signal in time. Yeah? So we'll run some perceptual experiments when we will show natively using G-Sync option of an NVIDIA card. We can render frames with any frequency we want. And then we will apply different displacement for 48 frames per second. And we'll ask users when the appearance matches the best. And as the outcome of this experiment, we will get such a curve. Yeah? So for emulated frame, to achieve certain emulated frame rate, we need to come with certain amount of displacement in temporal domain. So now we have function, and now director wants 27 appearance of equivalent to 27 frames per second. We look into this graph and we design shift in temporal domain of our frame. So here is like a standard solution versus our solution in terms of continuous and smooth transition from 24 to 48 frames per second. Ideally, I would need to have this projector calibrated to 48 Hz, and this would be best visible. So that's maybe less convincing. This would be less convincing. But we made this presentation at SIGGRAPH, and we really ask for calibrating display, controlling this frame rate, and I believe people could see. But I guess you grasp the idea. Yes, so in principle, we can control, in terms of appearance, frame rate. Let us move again to spatial resolution. Let's finish with time. Let's go into spatial domain. What you see here is a magnified view of cones in your fovea, and this red grid corresponds to pixel size, assuming that you look at high definition display at your desktop situation. So observation is that it's relatively easy to produce high resolution images because our cameras easily provide 20 megabits, megapixels, and so on. Yes? So kind of bottleneck is display. So our goal would be to show on the display more details than actually comes from resolution of your image. Yes? So we have our high resolution image that we would like to see. We will decompose it into temporal domain. And then there is one caveat, we need some motion. So either this should be video, something is moving, or we need artificially introduced motion. And when we introduce motion and we display those specially prepared images in temporal domain, our eye will integrate the signal and will get impression that we reproduce details beyond resolution of pixels. So let us try to understand why we need motion. Yes, so again, let's assume that this is projection of our cones onto pixels on the screen. Let's look what kind of signal would be integrated over cones ABC. So pixel is blue, C cone is this green pixel, some signal is integrated, we change color, we do it 3 times, and pixels A and B, they integrate, they set the same signal. That's static situation, yes? That's not something that we want. Let's consider now dynamic situation, yes? So I shift the image, and you track it because you want to look into certain details in the images. We have 3 photoreceptors. What kind of signal is integrated now, yes? So we have this continuous motion of those photoreceptors, they slide over the screen, and at the same time, in temporal domain, we change image content, and then at the end, each photoreceptor integrated slightly different signal, yes? And what signal was integrated, we can predict. This is weighted average of displayed pixel color and the length of path over the pixel that those photoreceptors make, yes? So what kind of photoreceptor pattern I have in my eye? This I don't know. So I will do simplifying assumption. I will assume that photoreceptors are just a grid of reasonable resolution, yes, corresponding to the distances in the human eye. And then for each of photoreceptors, I will try to predict integrated signal, these virtual photoreceptors, assuming that I know exactly their trajectory over screen. So this boils down to overdetermined set of equations when this vector corresponds to pixels in this high-resolution image. This matrix W corresponds to weights, so each photoreceptor had certain set of weights corresponding to the length of the path. And then what I need to find, I need to optimize for those frames that are displayed in temporal domain. So those frames are of resolution of your display, yes? But by integrating them, you observe the image that you see, this desired image of high resolution. So this is the outcome of this optimization. You see a lot of high resolution. You see a little scrambled pattern, optimized, and when you integrate this pattern in your eye, you start to be able to read very tiny text. Just to say that I need a mask 2 by 3 pixels to reproduce whole alphabet. So that's cheating, yes, because in temporal domain I will use this mask 3 times. So in fact I will have 3 times 2 by 3. This is what would happen. Let us switch to stereo vision for a while. And kind of quick refresher. So we have screen, we have 2 eyes. We have certain disparity. So image between left and right eye is shifted. then we verge, and we see this object in this particular place. Our eyes are verged in order to fuse these images that you don't have their image. And there is one problem in that. Yes, the problem is that we verge a certain distance from the screen while we accommodated the screen. Yes, so that's different than what happens in real world. And quite nicely, we have certain tolerance. 0.3 point diopter is our tolerance. This is called depth of focus, and that's good. Yes, because if we would require to be focused with high precision on every object, and immediately we would see that we are the focus, then the quality of seeing would be deteriorated. Yes, but because of this tolerance, lens in the eye accommodates a bit earlier before we reach this boundary 0.3 point diopters. Yes, and we see image good quality and always sharp. But nevertheless, this tolerance. Yes, so when our objects are placed in terms of accommodative power, plus minus 0.3 point diopter from the screen, everything is fine. But where we achieve viewing comfort, and we would notice much a problem. The problem is that objects in space can be located arbitrarily, yes? And then, of course, we need to compress them to bring them into this comfort zone. So compression, compression of depth. I have some background in doing tone mapping operators in high dynamic range imaging. That's something that I know how to do, yes? I will use whatever compressive function, or I will go into more sophisticated operators. And instead of compressing contrast, this time I will compress just disparity. So that would be very similar to tone mapping. So now my task would be how to do such compression in an informed way. Yes? So I have a real-world situation, and I have my depiction on the screen, and I would like ideally to have similar impression, or if I cannot reproduce a similar impression of depth, I would like to know what kind of error I make in the reproducing depth. So we would need to have some guidance over our disparity compression. Let us consider sensitivity to depth. Yeah, so we have two objects located at different depths, and my question is this difference of depth noticeable at all? Because if it is not noticeable, I can easily compress. Yes? Or if it is noticeable, how significant is the difference? Yes? So I have a large depth, I compress it, and how much depth I change, how you see it. Yes? I am not interested in absolute numbers. So we come to detection threshold, but typically you would read it in the context of contrast. This time we are talking about depth. So how much I need to change depth in order that I have just noticeable depth difference, that I am able to detect that depth was changed. So I can perform such experiment for depth corrugation, so for some surface with different frequencies, and I get this inverse this U-shaped curve, which is called disparity sensitivity function. The highest sensitivity comes in the range 0.1 to 1 cycle per visual degree, and everything below signal with lower amplitude of corrugation remain imperceptible. There is an analogy to contrast sensitivity function. Maybe many of you are familiar with this. Here, contrast sensitivity is highest for 4 to 10 cycles per visual degree. So this is 1/10 of order of magnitude shifted with respect to depth. Here we have 0.2 to 1 cycles per visual degree. So that was detection threshold. Let us talk a little bit about discrimination threshold. And that's more interesting. I already have certain depths, yes? And I want to know how much I can compress this depth or expand this depth before it starts to be noticeable. So the difference is I don't start from ground zero, I already have some corrugation, and I enhance those corrugations. So the magnitude that I can add before it is noticed depends already on existing magnitude. But I would like to do a formal experiment. So sensitivity to depth would depend on frequency of those corrugations, and also on existing magnitude of corrugation, on amplitude of those corrugations. So essentially that's my domain. I select some sample points. For each sample point I perform measurement. Each sample point is associated with certain frequency at certain amplitude. I measure thresholds, and these thresholds are measured when you deal with stereo. You use random dot stereograms. You want to eliminate all cues, just focus on disparity. And there are some methods essentially to very precisely determine such thresholds. So at the end, you get some analytic function, and this analytic function would tell you, for given disparity, what is the response of human visual system. So how sensitive I am for changes of disparity. So this function is compressive. This would mean that for small disparity values, I will be relatively sensitive for small changes of disparity. A little bit like Weber law, yes? Where for large disparity values, I need to increase or reduce disparity significantly, and then I will be able to notice the difference. And that's good news for me, yes? Because when I have large disparities, I want to compress them a lot. So what I will do now is I will take my input image, I will use this family of transducer functions, and I would convert my physical vergence into some hypothetical perceptual space. I would bring it into space which is scaled according to response of human visual system. Yeah, so now I am in this perceptual space, and now rescaling by some factor is meaningful. This means that equally, irrespectively of disparity value, everything would be rescaled in meaningful for human perception way. So I come back now to my question. Yes, I have original image and original depths, and I can decompose it into different frequency bands. And I have my process depth. I can do the similar thing. I convert it using this transducer, and I calculate the difference. So that's for me kind of the error. Yes, perceived error in terms of reproduced depth. And I can represent this error as a map. And now I know that maybe in one white regions, my depth compression is too strong. In terms of perception, this is the most critical. And maybe I need to change parameters of my depth compression algorithm. So what are kind of practical applications? One practical application could be that there are different devices, display devices, and they have different quality. There is different crosstalk. There are many factors that affect how good you perceive depths when it is reproduced on such devices. And different users, they have different sensitivity also for depth. So what I can try to achieve, I can personalize depth. Yeah? So I have certain image. I know sensitivity of this guy because I measured, and that measurement was done on a shutter glass device. I go into this neutral perceptual space, and through inversion of my model, I will consider sensitivity of this another person to depth, and the fact that he used anaglyph devices, and I will get new family of disparities, and the net effect would be that perceived depths by those two gentlemen should be very similar. So irrespectively of equipment and irrespectively of personal sensitivity. One more interesting trick that can be done is, this is typical anaglyph image, and of course we don't enjoy seeing it. We are in the situation of the guy at the bottom, but quality. Now of course we can see the image, but the guy, if it would be such a guy in this room in glasses, would not enjoy a lot. Yes? So what we can try to do is a single depiction make happy both persons, but with some trade-offs. You notice that close to the edges, I have a little bit of this anaglyph pattern. I have a little bit of disparity. And what's the trick? The trick is, again, this is why I recall this, Cornsweet Illusion. So Cornsweet Illusion, I demonstrated at the beginning for luminance, but Cornsweet Illusion works also for depth. If I would have a block of wood shaped this way, yes, with such profile, and I would show it to you, you would say this part is closer, this part is farther. So the same receptive fields, similar neurons process signal, there is some discontinuity of depth, and then you fill in. Yes? And this filling in effect was used in this case on the boundary. We introduce small Cornsweet depth discontinuities with Cornsweet profile. They fall off very quickly to zero, and we can cascade this effect. Yes? So I introduce one Cornsweet effect after another, and your brain tries to find some explanation. Yes, this is deeper than this hand. Yes, and this hand is deeper than this hand, so this hand must be much closer than this hand, yes? Your brain would try to make sense out of it. This is why you would build mentally this depth image. Still stereo 3D and reflections and refractions. Maybe sometimes when you look into some refractive object, you didn't feel comfortable. And why it is so? Because of so-called rivalry. So left eye and right eye would see slightly different image. This is kind of exaggeration situation, but we do sometimes such experiments. We show something completely different images on to two eyes. And still your brain would try to make sense out of it. It cannot make sense of such diverse images. This is why you will get some instability. You will see for a certain moment of time vertical bars, and then they will be replaced by horizontal, and so on and so on. Brain will work hard to make sense out of it. For transparent objects, and here I use convention, I show image for left and right eye. You see that those images are quite different. And that's not super comfortable situation. That's called rivalry. So let's look into highlights, yes? So those are highlights, and patterns that are seen by left and right eye change quite drastically. Some parts disappear, they change essentially shape. And this causes rivalry. Yes? So what movie manufacturers would do, they would glue this highlight pattern to the surface for you. Yes, so essentially they say, okay, we don't want to have any compromise that you complain about quality. We'll attach it to the surface, you will be happy. Yes, but then in terms of appearance, of glossy appearance, this would be less convincing. This would be looking less glossy. So what can be done? First, maybe let's explain why, what happens. Yes, so we have two eyes, we have this sphere surface, and we can verge our eyes on the surface of the sphere, or we can verge our eyes on virtual image. Yes, so again, this situation that's a little bit uncomfortable, that you have like one screen and another screen, and if they will be, again, in the optic sense, separated too far, that would be not comfortable experience for you. And for convex objects, very similar situation. So what we would like to achieve is we would like to get relatively stable patterns, reduce this rivalry, and we can achieve it by relatively simple trick. What we need to know, and we know it from landmark Eric Reinhardt and Kahn paper, that we are not super sensitive for highlights, for transparent objects. Something that looks plausible, we buy as more or less working okay. So we take advantage of it, and we separate, and in rendering it's relatively easy. In photograph content it would be more difficult, separate highlights. And then essentially by shifting highlight image, by controlling disparity for highlight image, we can place them wherever we want with respect to the surface. Yes? And we will typically place it just a little bit under the surface. This is why we would call it micro disparity. So that's exactly the situation. I have recovered highlight. I warp it a little bit just to shift it a little bit with respect to the surface. This pattern I add back to diffuse part, and the image is ready. Situation would be more complicated when in ray tracing style we need to consider not only highlight but refractions. All those effects cause this lack of comfort. And again, you can, like in ray tracing, go level by level of reflection and refraction and introduce a little bit of micro disparity in controlled way, and then effect would be satisfactory. One more thing about stereo. This time I would like to focus on scene cuts. So that's piece of movie, and that's typical situation. You have one scene, then there is cut, another scene. That's nothing unusual. Through saccadic eye motion, I shift my attention from object of interest in one shot and go into object of interest in another shot. So hypothetically, face of this guy and some moving guys in the background. So saccadic eye motion is enough. Saccadic eye motion is relatively fast. It takes between 20 to 80 milliseconds, and we are done. The extent of time depends a little bit on angular extent of saccade. Please notice that both eyeballs rotate in the same direction. So mechanically, that's more desirable situation. Now let us look into stereo 3D. The same scene, the same cut. What is the situation? So this character is in front of the screen, yes? So we need to verge our eye. The order of those two circles is different than for the background when we don't need to cross our Vergence eyes. We look behind, yes? So we already see that that's relatively complex, yes? We need to reverge, and while doing also saccade, because it's different part of the screen. So in terms of eyeball motion, please notice that our eyeballs rotate in opposite direction, yes? This takes significantly more time. It's more costly. So why this in real world we don't care, yes? But when we, for 2D movie also we don't care too much, yes? But stereo 3D movie makes situation a little bit more complex. Because for 2D movie we just do saccade, for 3D movie we need to do saccade and reverge. In the real world we get used to what may happen next, yes? In this room I am looking here, but through periphery of my eye I roughly know the depth of the wall, yes? And when I need to do saccade I'm kind of prepared. Everything mentally in my brain, I have the image of this interior, yes? When you have cuts in the movie, directors want to typically surprise you, yes? You don't know what will be next cut. You need to understand scene from the beginning and initialize this saccade and vergence from scratch, yes? Here, these things is much more smooth. This is why it's quite a different situation, and if I tell you, maybe you would not believe. So here is some statistics on time between cuts in movies and how it changes as a function of time. Yeah? So even in 30s, there was maybe about 20 seconds of distance between subsequent cuts. That was already relatively, I would expect that shots are longer. Now we are, average is around 4 seconds, and that's Rocky 4, but Mission Impossible 2 is, time is below 2 seconds between cuts, yes? Why directors do this? Yes, because they want to keep us involved, yes? They don't want that we drift, that we look in uncontrolled way. They want to fully control our attention, yes? This is why through narration they will change those shots very quickly, that they control exactly where we look and what happens. So now if I tell you that revergence time is between 400 to 700 milliseconds, and if you have for the distance between the time between two shots, 2 seconds, not much time remains to see something, yes? Because when you reverge, you have diplopia, you have blurred image, you have not good quality image. So essentially, one way is shot movies more carefully or change habits, allow for longer shots. Directors would hate the idea, yes, that they are forced to do something. So maybe we should be a little bit more careful. And how we prepare this 3D movie. And for this purpose, we wanted to understand, yes, what is the relation of this vergence time depending on current fixation point and new fixation point. So very simple experiment with stereoscopic eye tracking. So eye-link device, 1000 Hertz was used. So each eye is sampled with 500 Hertz. So we know pretty well what happens, yes? And we choose some starting position and we change in-depth position of our stimuli, and we essentially get such characteristics. So this is recording for left and right eye. Here you clearly see that that's saccade, yes, because both eyes rotate in the same direction. Yes? Here is vergence because there is this, they rotate in opposite direction. You see also that the time is much longer. So we just measure this time, and the outcome was as follows. Yes? Going outward screen, time is a bit longer. When you are closer to screen, this time is a bit shorter. When you go towards screen, even if you are farther fixated, time gets shorter. So you can imagine we have some model. For any starting and any position, we know how much time does it take. So that's like a big picture of this model. Yes, going inward towards screen is faster, going outwards is slower, and the farther you are, the slower it is. So what we can do, yes, we have this situation from this example that I showed at the beginning. Here is face of this character in front of the screen, and then there are these running guys behind the screen. there is a big difference in depth. What we would recommend to director is just possibly place them all object before cut and after cut, object of interest at similar depth. But sometimes it's not possible because we don't know whether we look on one object or another. Yes? So we maybe need to make some decision how to place the whole scene with respect to screen. And this we can do essentially by kind of virtual rotation towards inwards to cameras. Or we can magnify depth by increasing or reducing baseline between cameras. I would like to say a few words also about eye tracking. So there was today one paper when we discuss like optimal sampling in spatial domain. I would like to talk about eye tracking in the context of depth perception. And again, eye tracking, machine learning is coming. Yes, they claim that they get better results. When you drive a car, they would like track to your eye. This technology definitely will be kind of commodity. And in HMD, you have eye track. This is a copy of slides from earlier presentation, but not about contrast, discrimination contrast as a function of eccentricity in your retina, but this shows you sensitivity to depth as a function of eccentricity in your retina. Yes, so the farther from fovea, sensitivity is reduced. So what we would like to achieve? We have seen with certain depths, we know already we need to compress these depths to get Vergence accommodation conflict, but now we know that we are looking at the rabbit. So why not expand the depths for the rabbit and compress everything else? And when I switch to another character, I do exactly opposite operation. Yes, expand depths of this object. And you notice maybe, or maybe it was difficult to notice, I move also rabbit close to screen, and I try to move this guy also closer to the screen, because that's the most comfortable situation. Accommodation perfectly agreed with Vergence. But I would like to do this in seamless way, and that's the most interesting issue and most difficult problem, and low cost. We use in this project 100 euro eye tracker. That's original kind of function that takes input disparity and then we get output disparity. And what we would like to achieve is in the region where we look, yes, have this kind of S-shaped function for compressing disparity. So essentially extending in around the region where we gaze. Yes, and now we have a situation that we gaze in another direction and we would like to get this curve. Of course, if I would switch from one curve to another curve, you would see some jump in the image. So the idea here in this project is to do this relatively slowly. So this is shown here, yes. I change gaze direction and then two things happen, yes. I essentially expand depth around newly gazed object and I also shift it a little bit toward the screen. So always the point where I gaze, I try to move closer to the screen. So now I need to measure essentially speed with which I can go from one curve to another in such a way that you don't notice it. And it turns out that you are not super sensitive for changes in disparity. You will be very tolerant for this. So essentially we would have in mind, again, two same operations as in the context of this cut, yes? So we can change position of our object with respect to the screen, which translates into moving higher and lower this curve. We have input disparity and output disparity. And then we have relative disparity manipulation. Yes, so I mentioned I change distance between baselines in one incarnation. Here I just warp my images. Yes, and then I can control slope. So I have two operations to control. I need to measure now what is maximum speed that I can perform change of the slope or shifting this curve in such a way that you would not notice. Yeah, so essentially experiment will be very simple. Random dot seriograms, some corrugations, and I change those corrugations with different speed. And I see when you are able to see it. Yes, so essentially I go from one corrugation to another in smooth way with different speed, and then I get your characteristic. Once I get your characteristic, I essentially plug it into the model, and this model already knows how quickly I can do it, and that's a recording session from iChat. So now coming back to movies, I can help director in the way that here what you have here is kind of saliency map. The directors typically know where you look. And then I would like extend depths in the regions where most likely you would look. Yes, I can do this using this technique that I presented frame by frame. Then I would get tons of such curves. But that's maybe from frame to frame, the distance between those two curves would be too big. So I will run a small optimization just to make them coherent as a function of time. And then essentially, okay, I should get better results. Two short topics. These things is moving, okay, nothing special. But when I have rigid motion between front and background, you clearly see that something is going on in terms of depth. Yes? And now my claim would be, okay, this airplane, there is not much rigid motion within airplane. So I would add a lot of depth to airplane, and there is a lot of motion parallax between airplane and those buildings, and between buildings themselves. So maybe I don't need to allocate that much disparity, which is precious resource, because motion parallax will make impression of depth, and this is what I want. Yes, so essentially, that's exactly what happens. That's input situation, and then I notice, okay, there is motion parallax between buildings, so I allocate more depth for airplane, and this is what I do. Again, I would like to do this in an informed way. This is why I will run perceptual experiment. This time I would like to know how much depth arise from motion. Yes? So what is impression of depth that arises from motion parallax? So what I will do is I will have this dynamic object, and now it's blinking because I show it for the left and right eye. And I will ask you the question where you see comparable depths for static disparity. So I will find equivalent depth perception for disparity plus motion parallax versus just static disparity. Yes? I will get some characteristics like that. There will be we will run matching experiments. I will get some curve. And now I know essentially, yes, how to replace disparity by motion parallax. What is interesting in this graph is that this line, this red line, corresponds to real-world situation. Because in the real-world situation, when I rotate this, I have some rigid motion of this object, yes. There is one interpretation. There is motion parallax, but there is also depth that comes directly from this geometry, yes. In virtual situation, motion parallax comes from 2D pictorial cues. I cannot change it. But disparity, but depth I can change through disparity. So real-world is this red line. And this is what people investigated so far. We investigated those situations when you have a combination of disparity that is virtual, that is already compressed. And then you have this full space. The last thing that I would like to mention, I had slides, on initial slide accommodation. Yes? And that's kind of interesting cue. And we tried to reproduce it by building some custom display together with NVIDIA and North Carolina Chapel Hill group of Henry Fuchs. So that's kind of device, a little bit primitive. That's good that we don't have sound because that's pneumatic device, so makes a lot of noise. Essentially the idea is, let me roll it maybe again quickly, that this is kind of see-through display that has eye tracking and accommodates, so show this virtual image at the depth you want. Yes, so we can control it this way. So what happens? That's a very simple device. Yes, I mean you will not have it in home. Yes, I mean that's not technology that would take off, but we build it because we are interested in interaction of all those cues plus accommodation, which was so far not so well investigated. So essentially we have this display, this screen at the top of head, and then we have this mirror that changes shape. Yes, so very simple idea. And through change of shape, we can control position in depth of virtual part. Yes? So that's kind of interesting device because we see real world and we can compare real world with virtual world while having this accommodation cube. So here is how this membrane works. It's controlled by pressure of air. The time to get full range of depth is below 200 milliseconds. Sounds a little bit scary. But when I look into how quickly we do accommodation with our lens, you will be a little bit disappointed. To initiate it at all, you need around 300 milliseconds. And then, depending on the range of change of focus, the whole process may take up to 1 second. So this means that we are significantly below, I mean, we are faster than human lens, so that's fine. I will conclude maybe at this point, and what I would like to be kind of message to take home, yes? So knowledge of perception can be a significant factor towards improving apparent image quality. And we discussed, I gave you some example concerning spatial temporal resolution, perceived depth, yes? I was trained that way, and maybe some people in this room, when you do everything like physically correct, physically based lighting simulation, that nothing may go wrong, yes? But actually I showed with those highlights, yes, that when you have crippled displays, then maybe sometimes you should allow for some depart from physical correctness, rather micro disparity than fully disparity, in order to balance perceived quality and comfort. So cinematography with stereo 3D is kind of difficult problem, and maybe it didn't really take off. But also, when you look into statistics, the number of titles that is in stereo 3D does not drop. It's constant, it doesn't grow. Yes, it didn't replace 2D, but still certain amount of titles is done in 3D. And the idea is, the more you reduce gap, the more comfortable situation you will create by displaying such content, the more maybe it would be more popular. And of course, in the context of virtual reality or augmented reality, we cannot escape for stereo 3D. We ideally would like to have those cues. And eye tracking looks like simple idea, but think about it. Yes, it will be commodity device. As I mentioned, you will have it in every car. It would control where you look, what you do. And it's maybe worth also to think a little bit about new applications. Many cues that I showed so far, I still consider it in isolation. I tried to combine like disparity plus motion parallax, but I didn't combine disparity, motion parallax plus accommodation. So maybe some of those models that I presented is just scratching the surface. There are still many interesting things to be done. And here is the team of people with whom I did this work that I presented, with some of them more in the past, some of them are more recent PhD students. There are some, not Slovak accent, but at least Czech, Petr and Martin Čadik, maybe some people you know. So I would like to thank you for your attention.